clock that has never been wrong. There is a particular kind of quiet that arrives very late, when most things have wound down, and the ones that haven't are just humming at a frequency you stopped noticing an hour ago. You are probably horizontal or close to it. Your body is doing something right now that it does not ask permission for. Your heart is beating at a rate your brain did not choose. Your cells are cycling through processes that began before you were born and will continue without your input until they don't. None of this requires your attention. It never has. Something about that is worth sitting with before anything else gets said. This is Sleepy Science Channel. If you are here because someone sent you this, or because an algorithm noticed something about the hour you tend to be awake, that's fine. You don't need to have found this on purpose. There are people who help keep this going, and every time a new chapter gets made, there is a moment somewhere in the middle of writing it where the fact that those people exist feels less like support and more like permission. That's not a small thing. And if you ever feel like sharing this with someone who tends to be awake when they shouldn't be, that would be enough. There is a clock somewhere that has never been wrong. Not a clock anyone built. Not a clock anyone set. Just a process, a rate at which something happens relative to something else, that has been running since before the first measurement was taken, before the first number was assigned, before anyone decided that counting time was a thing worth doing. You cannot see this clock. You cannot hear it. But your body knows it the way your body knows hunger, not as a concept, but as a condition. You age. Your cells divide, and then divide less cleanly, and then stop dividing. Your hair goes. Your eyes adjust more slowly in the dark. Time is not something that happens around you. It happens through you, the way current moves through wire, the way pressure moves through water, directional and indifferent and continuous. What physics eventually had to admit, slowly, with considerable resistance, is that this clock does not run the same way everywhere. Not slightly differently. Not in ways too small to care about. Differently in ways that accumulate, ways that become measurable, ways that two clocks placed at different heights above the Earth will disagree with each other after a single day if you measure carefully enough. And we do measure carefully enough. We have for decades. The clocks disagree. The reason they disagree is not a malfunction. Follow this thread carefully, because it is thin and it goes a long way. Gravity is not a force in the way a push is a force. That sentence sounds like a technicality. It is not a technicality. It is the thing this entire chapter is trying to approach from a distance before getting any closer. When something massive sits in space, a planet, a star, a thing with enough weight to matter, it does not reach out and grab the objects near it. It changes the geometry of the space around it. And because space and time are not two separate things, but one continuous structure, space-time, a word that still sounds coined, but was arrived at through mathematics that had no other option. When space curves, time curves with it. Time curves. Not bends as a metaphor. Curves as a geometric fact. The rate at which time passes is slower closer to a massive object and faster further away. Your feet age more slowly than your head. By an amount so small you will never feel it, but by a real amount, a measured amount, an amount that GPS satellites must correct for, or they would drift out of accuracy within minutes. Your feet are older than your head by a smaller margin than you can imagine, and they have been since the day you started standing upright. This is the thread. Hold it. A clock is just a process with a rate. Your heartbeat is a clock. The decay of a cesium atom is a clock. The oscillation of light between two mirrors is a clock. Any process that repeats at a measurable interval is a clock, and all of them, every single one, run slower when they are deeper in a gravitational field. Not because gravity interferes with the mechanism. Not because something is pushing on the gears, but because time itself is running slower there. The clock is not wrong. Time is doing something different at that depth, and the clock is accurately reporting what time is doing. The deeper you go, the slower it goes. A clock at sea level runs measurably slower than a clock at the top of a mountain. The difference over a single day is roughly 30 microseconds, a number that sounds small until you learn that the system handling your location from orbit corrects for exactly this difference, constantly, because without that correction, the error compounds fast enough to matter. Gravity does not slow clocks. Gravity is what time does when space has enough mass nearby to have an opinion about geometry. There is a way to feel this without the mathematics. Think of being very tired. Not sleepy, tired in the way that makes an hour feel like 10 minutes, or 10 minutes feel like an hour, inconsistently, unreliably, in a way your body experiences but cannot explain. You already know at some level that time does not move at the same rate across all conditions. Your body has been telling you this for as long as you have had a body. Physics arrived at the same conclusion, but it needed different equipment. The equipment confirmed what the tired body suspected. Time is not a constant. It is a rate. And rates depend on conditions. The condition that matters here is depth. How deep are you sitting in the well of something massive? The deeper you are, the more space-time curves around you, the slower your clock runs relative to a clock further out. You, reading this, are sitting at the bottom of Earth's gravitational well. You are deep enough that your time is measurably slower than it would be if you were floating in open space far from any mass. Not dramatically, not in a way your body registers, but the difference is there, accumulating, the way small things accumulate when given enough time to do so. The clock that has never been wrong is not a device. It is the rate at which time passes at a given depth in a given gravitational field, and it has been keeping accurate time since before anyone was around to read it. What changed is not the clock. What changed is that we built instruments sensitive enough to hear what it was saying, and what it was saying turned out to be stranger than expected. Not wrong. Never wrong. Just describing a universe where time is a local condition, not a shared one. Where two people standing at different heights are, in a real and measurable sense, living in slightly different rates of time. Where the word now does not mean the same thing at sea level as it means at altitude. Where the deeper you go, the less time agrees with everything further up. That thought has not finished arriving yet. That is fine. It does not need to arrive all at once. It has been true for the entire age of the universe, and it will still be true tomorrow, running quietly, accurate, patient, the way the oldest clocks tend to be. Not because they are slow, but because they have nowhere else to be. There is a moment. It arrives without warning, and it does not stay long. You are reading something, or someone is explaining something, or you are sitting quietly and a thought is making its way toward you from somewhere you cannot locate. And the idea is almost there. Not arrived, not understood, just arriving. Like a sound you heard in another room that you are still deciding whether you actually heard. This chapter lives inside that moment. Not the understanding, not the explanation, the threshold. Physics, it turns out, has a shape that the body recognizes before the mind does. This is not a metaphor. There is research suggesting that the body begins preparing for a correct answer slightly before the reasoning process delivers it. A kind of anticipatory state, a leaning forward in the nervous system, as if the biology knows something is about to land. You have felt this. You may be feeling it now, if the previous chapter left something unresolved in you, which it was designed to do. The thing that is arriving, slowly in this chapter, without being rushed, is the shape of the relationship between space and time. Not the mathematics. Not yet. The shape of it. The way it feels to hold in your mind once it is there. Think about something you understood once that changed the way other things looked afterward. Not a fact, not a piece of information. A structural shift, the kind where, once it happened, you could not remember what it felt like to not know it. The way depth perception works, once you understand it, you cannot look at a painting without being slightly aware of how it is lying to your eyes. The way you cannot unhear a wrong note once someone points it out. Understanding the relationship between space and time does that. It changes the texture of ordinary things. Not dramatically. Quietly. The way a room looks different after you have been told something important happened there. Before Albert Einstein published his theory of special relativity in 1905, space and time were treated as separate containers. Space was where things were. Time was when things happened. The two were related only loosely. You needed both to describe an event, the way you need both a street address and an appointment time to be in the right place at the right moment. But they were not made of the same thing. They were two different kinds of measurement applied to two different kinds of reality. This felt correct. It felt correct because it matched everything humans had ever experienced directly. Space looks like space. Time feels like time. They do not look like each other. They do not feel like each other. Space is where your body is. Time is what is passing while your body is there. But here is what the threshold feels like. You are about to be asked to hold two things at once. The first thing is that space and time are genuinely, mathematically, physically, a single structure. Not connected, not interrelated. The same thing, described from two different angles. The second thing is that this is true even though it does not feel true, will never feel true in your direct experience, and the part of your brain responsible for navigation will refuse to accept it on a gut level, no matter how many times you encounter the mathematics. Both of those things are true simultaneously. And the threshold, the moment just before the understanding arrives, is the moment when you are holding both of them without yet knowing how to hold both of them. This is where this chapter wants to stay for a while. There is a physicist named Hermann Minkowski who, in 1908, gave a lecture that opened with a statement that is still, more than a century later, the most efficient way anyone has found to say the thing. He said that space by itself and time by itself were doomed to fade away into mere shadows, and only a kind of union between the two would preserve an independent reality. Not connected. A union. The way hydrogen and oxygen are not two things that happen to spend time near each other, but something that, when combined, is genuinely a different thing entirely. Water does not remember being hydrogen. Space-time does not remember being space and time separately. Your body, right now, is moving through space-time. Not through space. Not through time. Through the single structure that those words describe together. And the rate at which you move through the time dimension of that structure depends on how fast you are moving through the space dimensions of it. Slower through space. Faster through time. Faster through space. Slower through time. The total, if you could add them the way you add velocities, always comes out the same. Always. Without exception. For every object, everywhere, at every moment in the history of the universe. You are moving through time right now at almost the maximum rate possible. Because you are sitting still. Because almost none of your space-time velocity is being spent on space, nearly all of it is going into time. You are aging as fast as it is possible to age. An astronaut aboard the International Space Station, moving at roughly 7.7 kilometers per second relative to the surface, is spending a small fraction of that velocity on space, and so slightly less of it goes into time. They age more slowly, by microseconds per day, but by a real amount, a measured amount, an amount that accumulates. The threshold is this. You are about to understand that moving through space and aging are not separate phenomena that happen to coexist. They are the same budget. One account. Every meter per second you spend going somewhere is a fraction of a second per day you do not spend getting older. You have not quite arrived at that understanding yet. This chapter is not going to push you there. It is just going to leave you here, at the edge of it, in that particular feeling. The one that arrives just before something changes. The one your body recognizes before your mind does. The argument is over now. It lasted about 200 years. People fought about light the way people fight about things that matter. Not always productively, not always politely, and with a confidence on both sides that turned out, in the end, to be only partially deserved. While they were arguing, light did not wait. It kept travelling. At the same speed it has always travelled. Through the vacuum between stars. Through the atmosphere above your head. Through the lens of every instrument that was built to study it while the argument was happening. It arrived where it was going, slightly late to places with more gravity, as it always does, and nobody noticed for a long time because nobody had built a clock sensitive enough to catch the difference. Here is what the argument was about. Isaac Newton believed light was made of particles, small, fast, corpuscular things. He had reasons. The reasons were good. Christian Huygens believed light was a wave, a disturbance propagating through something, the way a ripple moves through water. He also had reasons. His reasons were also good. For roughly 2 centuries, the argument went back and forth. Experiments were done. Results were interpreted. People died defending one position, and the position kept going without them. What nobody fully appreciated during the argument, what only became clear much later, when the mathematics had caught up, is that both sides were describing something real. Light behaves like a particle when you measure it as a particle. It behaves like a wave when you measure it as a wave. What it is, when nobody is measuring it, is something that does not have a clean word in any human language, because human language was built to describe things at human scales, and light is not a human scale phenomenon. This is important to the chapter, but not in the way you might expect. The argument about light's nature is not the subject here. It is the backdrop. The subject is what light was doing the whole time. Light, in a vacuum, travels at 299,792,458 meters per second. This is not approximately that number. It is exactly that number. The meter is now defined in terms of it. The second is defined separately, through atomic clocks, and the speed of light connects the two definitions the way a single equation can connect two entirely different things and make them permanently dependent on each other. This speed does not change. Not for the source of the light. Not for the observer. Not because of how fast either is moving. A laser fired from a stationary platform and a laser fired from a ship moving at half the speed of light will both arrive at the same distant target at the same speed. Not almost the same, exactly the same. This is the part that broke 19th century physics. If you are on a train moving at 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour, the ball is moving at 150 kilometers per hour relative to the ground. This is how velocities add. It is how they have always added. It is how they still add for everything except light. Light does not add. A photon fired forward from a ship moving at half the speed of light does not travel at 1.5 times the speed of light relative to an outside observer. It travels at the speed of light. Same as always. Exactly. The reason velocities do not simply add for light is the same reason time runs differently at different depths in a gravitational field. It is the same reason, not a related reason, the same one. Space and time adjust themselves, contract and dilate in the technical language, in exactly the amounts needed to keep the speed of light constant for every observer everywhere. The universe is not bending the rules for light. The constancy of the speed of light is the rule, and space and time are what bend to protect it. Light was doing this the entire time. During the argument about its nature, during the 2 centuries of experiments, during every moment when a human pointed an instrument at it and tried to catch it being something in particular. It was travelling at the same speed, through a space-time that was adjusting itself quietly around every observer, keeping the number constant, never deviating. There is a consequence to this that most explanations rush past. If the speed of light is the same for all observers regardless of motion, and if space and time bend to keep it that way, then space and time are not independent. You cannot stretch time without compressing space. You cannot compress space without stretching time. They are coupled. The same way the tension in a string is coupled to its pitch. You cannot change one without changing the other, because they are not separate properties. They are aspects of the same physical reality, and light is what revealed that they were always connected, quietly, long before anyone had a name for the connection. In the same way that water reveals the shape of a container you might not have noticed was there. The argument about whether light was a wave or a particle settled into something more complicated than either side had imagined. Something called wave-particle duality, a phrase that sounds like a compromise, but is actually a description of genuine strangeness, a thing that is neither and both, depending on how you look, which is itself a lesson about the relationship between observation and reality that goes deeper than this chapter wants to follow right now. What matters here is simpler and older, and in some ways stranger than the quantum mechanics that wave-particle duality eventually led to. What matters is that light has a speed. That speed does not change. And the universe shapes itself around that fact, with a consistency that, once you see it, starts to look less like a rule and more like a definition, as if the speed of light is not something the universe enforces, but something the universe is, in the same quiet way that a circle is not enforcing its roundness, but simply being what it is, from every angle, without effort, without exception, as it has been since before anyone drew one. You have probably heard that gravity is a force. It was taught that way. It was in the diagrams. Arrows pointing downward, labelled with a number, describing the pull of the Earth on a falling object. The force of gravity. Measured in newtons. Calculated with a formula that still works, still gives accurate predictions, still tells you how fast something falls and where a thrown ball will land. The formula is not wrong. But what it is describing, what gravity actually is not a force. This is not a technicality. I want to say that again because it is the kind of sentence that sounds like a technicality and then turns out to be the entire point. What gravity is, at the level of what is actually happening in the physical world, is not a force. It is a geometric property of space-time. It is what space-time does in the presence of mass. And once that lands, if it lands, the way you understand almost everything else about how the universe works changes shape. Here is the thread. Follow it from the beginning. Isaac Newton, in 1687, described gravity with an equation that is still one of the most useful equations in physics. Two masses, a distance between them, a constant, and a number that tells you the strength of the attraction. It predicted the orbits of planets. It explained the tides. It was used to calculate the trajectory of the Apollo missions to the moon. It works. But Newton himself admitted in a letter that he had no idea what gravity actually was. He could describe it. He could measure it. He could predict it. He could not say what it was doing, or why it reached across empty space without any apparent mechanism, or why two objects separated by millions of kilometers would pull on each other through nothing at all. He called it action at a distance, and said that the idea seemed absurd to him, and that he offered no hypothesis to explain it. That phrase, "I feign no hypothesis," is one of the most honest admissions in the history of science. The man who described gravity most accurately for 200 years admitted openly that he had no idea what it was. Then, between 1907 and 1915, Albert Einstein worked out something that answered Newton's question. Not by replacing Newton's equation, by explaining what it was actually measuring. What it was measuring, what gravity is the curvature of space-time. Space-time, the single structure made of space and time together, is not flat. It has shape. Mass curves it. The more mass, the more curvature. And objects do not fall toward the Earth because the Earth is pulling them. They follow the curvature of the space-time that the Earth's mass has created around it. They are moving in what is called a geodesic, the straightest possible path through curved space-time. From the outside, it looks like falling. From inside the geometry, it is going straight. This is the part that I am not entirely sure I can give you without losing something. The mathematics holds it precisely. The sensation of it is harder. Think of it this way, and then immediately remember that this way is an approximation. Imagine a sheet of rubber stretched flat and tight. Place a heavy ball in the center. The sheet curves downward around it. Now roll a smaller ball across the sheet. It curves toward the heavy ball. Not because the heavy ball is pulling it, but because the surface it is moving across is curved, and following the curved surface naturally brings it closer. This is the standard illustration. It appears in every popular science book written in the last 50 years. It is useful. It is also incomplete in a way that matters here. The rubber sheet illustration shows how mass curves space. It does not show how mass curves time. And the curvature of time is, in some respects, the larger effect, at least at the scales we can feel. The reason you fall toward the Earth when you jump is not primarily because space is curved around it. It is because time runs slower at lower altitudes, and objects naturally move in the direction where time runs slower. That sentence is accurate. And it sounds like I invented it. I did not invent it. Objects in spacetime follow paths that maximize the time they experience, what physicists call proper time. Near a massive object, time runs slower. An object moving toward the Earth is moving toward a region where time runs slower, which means it is moving toward a region of deeper time curvature, which means it is following the path through spacetime that is, from the geometry's perspective, the straightest available. Gravity is not pulling things down. Gravity is the name humans gave to the experience of following a curved path through a curved geometry, in a universe where mass curves time as much as it curves space, and where what we feel as falling is, from the geometry's perspective, rest. A person in freefall, in orbit or falling from a great height, does not feel gravity. They feel weightless. They are, in the technical sense, in the most natural state available to them in that region of space-time. They are following the geometry. The person standing on the ground feels gravity. The ground is pushing them away from the natural path their geometry prefers. The force is not gravity pulling them down. The force is the ground pushing them up, preventing them from following the curve. This is what I mean when I say gravity is a preference. It is not a word Einstein used. It is not a technical term. But it describes something real. Space-time, in the presence of mass, develops a lean. Objects follow that lean not because they are pulled, but because following it is, in the geometry of things, the path of least resistance. The path that requires no deviation. The path that the universe, if it had anything like an inclination, would call straight. The thread ends here for now. Not because it has run out, but because where it goes next involves the same geometry bending not just the paths of falling objects, but the rate at which time itself passes. And that is a different chapter, for a reason that will become clear when you arrive there. For now, the force you have been calling gravity your entire life is not a force. It is what a curved geometry feels like from the inside. And you have been living inside it since the moment you arrived. 2 clocks are already running. They have been running since before this chapter began. One of them is sitting on a shelf, somewhere at sea level, ticking at the rate that sea level clocks tick. The other one has been descending, slowly, steadily, into a place where the gravitational field is slightly stronger, where the geometry of space-time is slightly more curved, where the air pressure is higher, and the distance to the centre of the Earth is shorter. Neither clock is malfunctioning. Neither clock is broken. Neither clock is being interfered with. They are simply in different places. And in this universe, different places have different rates of time. The first person to seriously calculate what this would mean in practice was not doing it because anyone asked them to. They were doing it because the mathematics of general relativity, once you followed it carefully enough, produced a number, a small number, an easy-to-dismiss number, that said the following. A clock placed at a lower gravitational potential will tick more slowly than a clock placed at a higher one. Not metaphorically, not as an approximation, as a physical fact, as real as the difference in air pressure between a valley and a mountaintop, as measurable as the difference in temperature between the surface of the ocean and its floor. The number is small. At the surface of the Earth, the difference in the rate of time between sea level and an altitude of 1 kilometre is roughly 1 part in 100 billion per day. That means a clock at sea level loses approximately 1 nanosecond every day, compared to a clock 1 kilometre above it. 1 nanosecond. A human being cannot perceive a nanosecond. The fastest human reaction time is somewhere around 150 milliseconds, which is 150,000 microseconds, which is 150 million nanoseconds. 1 nanosecond sits so far below the threshold of human experience that it does not exist, for all practical purposes of living a life. And yet it is real. And yet it accumulates. And yet the GPS satellites orbiting the Earth must correct for it, for both the gravitational time dilation from being higher in Earth's gravitational field and the velocity-based time dilation from moving so fast, or they would drift out of accurate positioning by kilometers within a single day. The satellites correct for Einstein's equations not because anyone finds them philosophically compelling. They correct for them because if they did not, your phone would tell you that you were standing in the middle of a river when you were standing on the bridge above it. General relativity is not an abstract theory that physicists debate at conferences. It is running, right now, in the background of infrastructure that billions of people use without thinking about it, making small corrections to clocks that orbit the Earth at altitudes where time runs faster, so that when the signal arrives at the ground where time runs slower, the numbers still agree. Now expand this outward. The Earth is massive, roughly 6 times 10 to the 24th kilograms, a number so large it has no useful human-scale equivalent, but it is not particularly massive by cosmic standards. The Sun is about 333,000 times more massive. A neutron star can be 1.4 times the mass of the Sun, compressed into a sphere about 20 kilometers across. A stellar black hole can be 10 to 20 times the mass of the Sun, compressed into a singularity with no meaningful size at all. As mass increases, the curvature of space-time increases. As space-time curvature increases, the difference in the rate of time between different depths in the gravitational field increases. Not linearly. The mathematics is more aggressive than that. The closer you get to the center of a sufficiently massive object, the more dramatically the rate of time changes with every small increment of depth, until, at the boundary called the event horizon of a black hole, time from an outside observer's perspective stops entirely. Not slows to imperceptibility, stops. An observer watching something fall toward a black hole would, in theory, never see it cross the event horizon. They would watch it slow. They would watch it redden as the light stretching out of the deeper gravitational field loses energy and shifts toward longer wavelengths. They would watch it become dimmer and more red and slower, approaching the horizon. Asymptotically, never quite arriving from their perspective, frozen at the threshold while the universe continued aging around it. From the perspective of the falling object, it crosses the horizon in finite time. It does not slow. It does not freeze. It falls through. This is the part that pulls the floor out from under the comfortable idea of now. Two observers, one watching from far away, one falling in, disagree not just about how long something took. They disagree about whether it has happened yet. For the outside observer, the crossing is always in the future. For the falling observer, it is in the past. There is no third perspective that resolves this disagreement. There is no universal clock that both of them are reading incorrectly. The disagreement is not a measurement error. It is a feature of how time works in a universe where time is a local property, where there is no single now that stretches across all of space, where every observer carries their own rate of time the way they carry their own heartbeat, privately, internally, irreducibly their own. Come back to the two clocks. One on the shelf, one descended to a lower place. When they meet again, when the descended clock is brought back to the same altitude as the one that stayed, they will show different times. The difference will be tiny, measurable only with atomic clocks sensitive to fractions of a nanosecond. But the difference will be real. The descended clock will have ticked fewer times. Not because it was disturbed, not because anything acted on it, but because it was deeper, and at depth, time goes more slowly, and it has been faithfully, accurately, without any error whatsoever, recording the time that it experienced, which was less. The two clocks agree on everything except the one thing that felt most certain, how much time passed. And they disagree because they were in different places, And in this universe, where you are is part of when you are. The clocks are not confused. We were. There is an experiment called the Pound-Rebka experiment, conducted in 1959 at Harvard University, in which physicists measured the gravitational redshift of gamma rays travelling up and down a tower 22.5 meters tall, 22.5 meters. The height of a modest building. They measured the difference in the frequency of light between the top of the tower and the bottom. The difference caused by the gravitational time dilation across 22.5 meters of vertical distance. They found it. The difference was there, exactly as Einstein's equations predicted it would be, across a distance shorter than many people's daily commute in a vertical direction, in a laboratory built inside a building on a university campus, using technology that was considered sophisticated in 1959, but would be considered elementary now. Time ran differently at the top of the tower than at the bottom. They measured it. They published it. The result has been confirmed many times since, with increasing precision, using increasingly sensitive instruments, and the answer is always the same. Deeper means slower. Always. Without exception. In every gravitational field that has ever been measured. From the modest pull of a 22-meter tower at Harvard University to the extreme curvature at the edge of a black hole, where time from outside looks as though it has stopped entirely. The two clocks began together. They ended differently. The universe kept both records faithfully. It always does. There are places, not many, not visible from here, not reachable by anything we could build, at any speed we could achieve, in any time frame that would mean anything to a civilization still counting its age in thousands of years. But they are there. Places where, by any honest accounting of what time means and how it behaves, and what the mathematics consistently and without ambiguity says, time has stopped. Not paused. Stopped. This chapter is going to approach them slowly, from far away, the way you might approach something that requires a certain amount of distance to see clearly, not because it is dangerous, but because getting too close too quickly flattens it, and what this is cannot afford to be flat. Start here. Somewhere between 30 and 40 light years from where you are sitting, there is a star called Tau Ceti. It is slightly smaller than the Sun, slightly cooler, older by perhaps 1 billion years. It has planets. Some of those planets orbit at distances that have been described, cautiously, as potentially interesting. If you were there, standing on one of those planets in whatever conditions exist there, you would look up at the sky at night and you would see a star. Yellowish. Unremarkable to the eye. 3rd or 4th magnitude, maybe. Easy to overlook. That star would be the Sun, and the light leaving it right now, at this moment while you are reading or listening, that light will not arrive at Tau Ceti for 30 years. The image of the Sun that an observer at Tau Ceti is seeing right now is not the Sun as it is. It is the Sun as it was 3 decades ago. The universe does not deliver the present. It delivers the past, at the speed of light, and calls it now. Hold that thought loosely while this chapter drifts somewhere else for a moment. There is a class of objects called black holes. The name is not quite right. They are not holes, and the darkness is a consequence rather than a defining feature. But the name has stuck because language often gets there before precision does, and by the time precision arrives, the word has already moved in and rearranged the furniture. A black hole forms when enough mass is compressed into a small enough space that the escape velocity, the speed you would need to travel to leave the gravitational field, exceeds the speed of light. Since nothing travels faster than light, nothing escapes. Not matter, not radiation, not information. The boundary at which escape becomes impossible is called the event horizon. It is not a surface. There is nothing there to touch. No wall, no membrane, no change in the appearance of the space around you. If you were falling through it, you would not feel it. You would not know from the inside that you had crossed it. But once you had, you would not be coming back. The event horizon is not a physical thing. It is a geometric fact, a line drawn by the mathematics of space-time curvature, past which the future, every possible future of every possible particle, points inward. Not some futures, every future. The geometry itself inside the horizon is oriented toward the center in the same way that the geometry outside is oriented toward what we call forward in time. Inside a black hole, toward the center is not a direction in space, it is a direction in time. You fall toward the singularity the way you fall toward tomorrow, not because you are being pulled, but because there is no other direction to go. There are supermassive black holes at the centers of most large galaxies. At the center of our own galaxy, the Milky Way, there is one called Sagittarius A star. It has a mass of roughly 4 million times the mass of the Sun. Its event horizon has a radius of about 12 million kilometers. The distance from the Earth to the Moon is roughly 384,000 kilometers. The event horizon of Sagittarius A star is about 30 times the Earth-Moon distance across. It is not small. At the edge of that event horizon, not inside it, not past it, but at the boundary itself, time, from the perspective of a distant observer, has stopped. A clock hovering somehow at the edge of the event horizon of Sagittarius A star would appear, from Earth, to have stopped ticking. The light leaving that clock would be so severely gravitationally redshifted that it would take infinite time, from our perspective, to travel any meaningful distance. The clock would appear frozen. The universe at that boundary has, from our perspective, already finished. There is something philosophically strange about the phrase, "from our perspective," when it is doing this much work. Because it implies that there is another perspective, the perspective of something at or inside the event horizon, from which things are not finished, from which time is still going, from which the universe is still happening in a present tense. Both perspectives are real. Neither is more correct than the other. The universe does not adjudicate between them. It simply continues, differently, at different rates, in different directions, for every observer that exists within it, without any single observer being in a position to call the others wrong. This is what it means to say that time is a local property. Not that different people experience time differently, in the psychological sense, that is true but ordinary. Not that time feels faster when you are busy and slower when you are bored. That is real, but it is not physics. What it means is that time, the actual rate at which physical processes occur, the actual number of times an atomic oscillation completes in a given interval, the actual count of heartbeats in an hour, this is different in different places. Different in different gravitational fields. Different at different velocities. Different by amounts that are tiny at human scales and become dramatic at cosmic ones, but that are always, at every scale, real. Come back to the beginning of the chapter. The places that exist. Not many. Not reachable. But there. The boundary of every black hole is a place where, from the outside, time as a rate of change has gone to zero. A place where the universe, in a meaningful physical sense, has already finished for any observer watching from afar. And inside, Past the horizon, in the region where no information can return, time continues, differently, toward a different future. Oriented in a direction that has no equivalent in the space outside. The universe does not have a single clock. It has as many clocks as it has locations. And some of those locations have clocks that, from where we stand, appear to have stopped. They have not stopped. We just cannot see past where they got to. And there is something about that, about the existence of places in this universe where time goes on invisibly, past a boundary we cannot cross, in a direction we cannot point to, that has not quite finished landing in me, even now. I am not sure it is supposed to. Inside every cell of your body, there is a clock. Not a metaphor, a real one. At the ends of your chromosomes, the long coiled structures inside the nucleus of each cell that carry your genetic information, there are sequences of repeating DNA called telomeres. Each time a cell divides, these sequences get slightly shorter. They are not getting shorter randomly or by accident. They are getting shorter because the molecular machinery that copies DNA cannot quite reach all the way to the end, and so each copy is fractionally truncated. When telomeres become too short, the cell stops dividing. It either enters a dormant state or it destroys itself in a process that is, in the cellular world, considered orderly. This is aging. Not as a metaphor, not as a feeling, as a molecular mechanism running right now in the cells of your body, counting down at a rate that depends on, among other things, your stress levels, your sleep quality, your diet, your exposure to certain environmental factors. And, though by a much smaller margin than any of those, on where you are. On where you are in a gravitational field. On how fast you are moving through space. On how much of your space-time velocity is being allocated to the time dimension versus the space dimensions. The cells do not know about general relativity. They do not know about space-time. They do not know about the Pound-Rebka experiment, or the clocks in GPS satellites, or the event horizon of Sagittarius A star. They are just dividing, and shortening, and counting. But what they are counting is time. Real time. Physical time. The time that physics says runs at a rate determined by position and velocity in space-time. Your body has always known that time is physical. Not in the sense of knowing it intellectually, in the sense of being it. Every biological process runs at a rate. Heart rate, respiration, neural firing, cellular division, hormonal cycling, sleep rhythms. All of these are clocks, in the exact same sense that the cesium atomic clock in a GPS satellite is a clock, a process with a rate, counting something, giving time a body. And all of them, every single one, would run at a measurably different rate if you were in a different place. Not differently because of biology, not because a different environment would change your stress hormones, or your diet, or your exposure to radiation, though all of those things are also true. Differently because time itself, the substrate in which all these rates operate, runs differently at different depths, in different gravitational fields, and at different velocities through space. Your body is not separate from this. Your body is inside it, the way a watch is inside a room where temperature affects the viscosity of the oil in its mechanism. Except that it is more intimate than that. The room is not affecting your body from outside. The room is time, and you are made of processes that depend on time the way a flame depends on oxygen, not as a resource to be consumed, but as the medium in which the thing is happening at all. Here is something that is true and that most people are never told. The astronauts who spent 6 months aboard the International Space Station aged slightly less than they would have on the ground. Scott Kelly, who spent 340 days on the station in 2015 and 2016, returned to Earth measurably younger than he would have been had he stayed. Not by much, by roughly 5 milliseconds. 5 milliseconds is not a noticeable difference. No human can feel 5 milliseconds pass. But it happened. It was real. His twin brother Mark Kelly, who stayed on the ground during the mission, aged 5 milliseconds more than he did. The effect at orbital altitude is actually a competition between two opposing forces. The ISS orbits at about 400 kilometers altitude, where Earth's gravity is weaker than at the surface, which means time runs slightly faster there, which means the astronauts should age slightly more than people on the ground. But the ISS also moves at about 7.7 kilometers per second. At that velocity, the time dilation from speed, from spending a fraction of space-time velocity on space rather than time, more than compensates. The velocity effect wins. The astronaut ends up aging slightly less overall. 5 milliseconds over 340 days. Small, real, measured. Now zoom out further. An astronaut travelling at a significant fraction of the speed of light, say 90%, would experience time dilation of a factor of roughly 2.3, meaning that for every year the astronaut experiences on the ship, 2.3 years would pass on Earth. At 99% of the speed of light, the factor is about 7. At 99.9%, it is roughly 22. At 99.999%, it is over 700. 700 years of Earth time for every year on the ship. This is not a thought experiment. It is not science fiction. It is the correct prediction of special relativity, confirmed by particle accelerators, where subatomic particles moving at near light speed survive far longer than they should, longer than their natural decay time at rest, because from the outside, their internal clocks are running at a fraction of the normal rate. Muons, particles produced in the upper atmosphere when cosmic rays strike air molecules, have a half-life of about 2.2 microseconds when measured at rest in a laboratory. They are produced at altitudes of roughly 15 kilometers and travel downward at very close to the speed of light. At their rest half-life, only a tiny fraction should survive long enough to reach the Earth's surface. But they do reach the surface, in large numbers, because from the ground's perspective, their clocks are running slow. Their 2.2 microseconds of internal time are stretched, from our perspective, to tens of microseconds, long enough to travel 15 kilometers and arrive at a detector on the ground. The muon does not know it is doing anything unusual. Its clock is running correctly for its situation. It is moving very fast, and so its time is moving very slowly relative to ours, and so it survives a journey that should, by any stationary accounting, be impossible. Your body, at its telomere level, at its cellular division level, at its heartbeat level, would do exactly the same thing, scaled up to biological machinery. Consider a traveller. Not a real one. There has never been a human traveller at these speeds. But consider one, a person on a ship, accelerating at a comfortable 1g, the same gravitational pull as the Earth's surface, so their body does not know the difference. At 1g of constant acceleration, a ship reaches very close to the speed of light within about a year of ship time. This traveller could, in their own biological lifetime, in the time their own telomeres count, reach the Andromeda galaxy. Andromeda is 2.5 million light-years away. In the time the traveller experiences, thanks to the time dilation of near light-speed travel, the journey would take roughly 28 years of ship time. They would be 28 years older when they arrived. Their cells would have divided a number of times consistent with 28 years of biological aging. Their telomeres would have shortened accordingly. On Earth, 2.5 million years would have passed. The traveller and the Earth both kept perfect time. Neither clock was wrong. Neither life was an illusion. Both experiences of duration were real, accurate, faithful recordings of the time that actually passed in each location at each velocity. The universe kept both records. It always does. Your body has always been keeping one of those records. The cellular machinery running in every nucleus, in every tissue, has been faithfully counting the time that you, at your velocity, at your altitude, at your position in the gravitational field of a medium-sized planet orbiting an average star in an outer arm of a spiral galaxy, have actually experienced. Physics took until 1905 to write down the equations. Your cells have been solving them since before you were born, without knowing what they were doing, because they did not need to know. They just needed to divide, and shorten, and count. The body was always doing physics. We were just late to realize that physics was something the body did. And what it was measuring, all along, in every organism that has ever aged, was time. Not the abstract time of clocks and calendars and the agreed-upon divisions of a shared experience, but real time, physical time, the time that bends near mass and slows with speed and runs differently in every location in this universe, patiently, accurately, without opinion, keeping the record of every moment that everything has ever actually lived through, in whatever corner of space-time it happened to find itself, at whatever depth, at whatever velocity, for as long as it continued to be anything at all.